So today we're learning about nuclear chemistry, and ignore the noise in the back. I'm sorry, it's my fish tank. It's where my turtle lives. Sorry. So there are three types of radiation: alpha, beta, and gamma. So alpha particles are positive, so they're attracted to negative fields. Beta particles are negative, so they're attracted to positive fields, and gamma has no charge. Alpha decay occurs when unstable isotopes try to stabilize by emitting an alpha particle. It's made of 2 protons and 2 neutrons. So I'll be showing a practice problem. So here we have radium, and our mass number is 236, and our atomic number is 88. So now we're gonna add this. This is the alpha decay, and that's what it looks like. You add this, and so we're going to take 4 away from the mass number and take 2 away from the atomic number. And this is the number we now get. So we're going to look at our periodic table at the atomic number, which is now 86, to find out what our new element is. So on the periodic table, atomic number 86 is radon. So that's what it converted to. Right here, radon. And so we went from radium to radon. Beta decay is a little more complicated. It's essentially the same thing, just with the different numbers, and there's 3 types: beta emission, positron emission, and electron capture. So this is an example of beta emission. So it's right here, this is the beta emission, and we have a 0 on top as the mass number converting part. And on the bottom, where the atomic number is converted, it's a 1, -1, so it'll be actually adding. So this 6, which is our atomic number for carbon, is going to add a 1, and then it'll become 7, and nothing will be added to this, so the 14 will stay a 14. So the number we get is 14 on top and 7 on the bottom. So now our atomic number is 7. So if we look at the periodic table, that's nitrogen. We're going to write nitrogen right here, and now our equation is completed. That was beta emission. Now we'll be doing positron emission. So this is what positron emission looks like. So we have nitrogen, and we're the 0 at the top for the mass number. It'll just stay 14, it won't change, but we have a 1 here, and it's positive, but it's actually going to make it go down 1. So it's kind of like flip-flop, I guess, to say. So it'll be going to a 6 instead. So now we're back to carbon like we were up here. So you see, it's like kind of the opposite. See how this kind of looks like beta emission, except you won't get the same product. So it'll go from 13 plus -1, and so it won't counter out, it'll actually go down 1. So then we'll have 12 at the bottom for our atomic number, and at the top it'll just stay the same, so it'll be a 26. And if we look on our periodic table, that is magnesium, and that is electron capture. So, and gamma radiation is just energy and doesn't have a mass or charge, so there will be no formula for that. So now I'm going to stop the video and let you practice on your own with the 3 practice problems. Okay, I just ate a banana. It was a really good banana. Anyway, so now we're doing balanced nuclear equations. So a balanced nuclear equation obeys conservation of mass and of energy. The total reactant must equal total product mass. The total reactant charge must equal total product mass. So this here is an example of a balanced nuclear equation. So now we're going to talk about half-lives. So every radioisotope has a specific rate of decay. It's measured by its half-life, and its half-life is the amount of time it takes for half of a sample to decay into new elements. So half-lives of isotopes can range from billions of years to fractions of seconds. So an example would be uranium-238 has a half-life of about 4.5 billion years, and polonium-214 has a half-life of about 165 microseconds. So those numbers are, they're a little different. They're kind of far from each other. Billions of years to microseconds, those are big number difference. So you can really see how they can range, the range that half-lives of isotopes have. So this is the formula to find half-lives. So A is the starting amount right here, X is the number of half-lives, and Y is the final amount. So this is like your product, like this is half, like this is the answer, Y is the answer. So I'm gonna do a practice problem. So let's say we're starting with 10 grams. So we're starting with 10 grams. How much is left after 3 half-lives? So we're given 10 grams and 3 half-lives. So Y equals, our starting amount is 10, and then we add our little 1/2, and then the number of half-lives is 3. So you put this in the calculator, and you just do 10. So what I do is I do 1/2 and like put the, third up to the third, and then I multiply what I get from this times this. And then you get, so that is your answer. So Y equals 1.25. So now we'll be talking about fission and fusion. So fission happens when isotopes are bombarded with neutrons. Fission is more common. Rather than alpha or beta decay, they break into daughter products. So with fissions, we can have chain reactions, and they occur when a neutron hits the nucleus of uranium atoms, or uranium nucleus splits, aka fissions. So these reactions release enormous amounts of energy. Think of a fission bomb, and this can be controlled in 2 ways. It can be controlled with neutron moderation or neutron absorption. So now we're talking about fusion, and fusion occurs when nuclei combine to form a nucleus of greater mass, which also releases huge amounts of energy. So fission releases a lot of energy, but fusion releases about 3.5 times more per unit mass than fission. So fission releases a lot more. Fusion releases a lot more, sorry. And fusion is not as common. I said fission is more common earlier because you don't really see fusion very often because it requires extremely high. So like I said earlier, fusion is not really common, but there is solar fusion, which is usually how fusion occurs. And it's when 2 protons fuse to form heavy hydrogen. So stars are the birthplace of elements. Through fusion reactions involving hydrogen isotopes, stars produce both energy and all the nuclear elements. So just to wrap up, fission and fusion. Fission is a very heavy nucleus split into a more stable nuclei of less mass, and it can result in chain reactions used in nuclear reactors. Fusion is a lighter nuclei, and they combine to form heavier, more stable nucleus. This is usually like the hydrogen bomb in stars, and it produces less waste.